Hello, so this is 2.2, inverse of a matrix. Now, before we talk about inverse of a matrix, let's do a little refresh on what an inverse means. Right, so let's start with just regular number. Let's say A is a real number. All right, so A is a real number, and we know that um, A to the power of -1 is the inverse of A. All right. That means when you multiply A times A inverse, you get the number 1, right? Which is the same thing as taking the A inverse multiplied by A. All right, so a quick example would be like the number 3, right? Multiplied by 1/3, that gives you 1. So these two number 3 and 1/3, we say that they are inverses of each other. And that's the idea of inverse in terms of real numbers. Okay, now we're going to look at inverses in the idea of matrix. Okay? So the idea here is first we need to identify what the number 1 is in matrix, right? So first we have the um, identity matrix. All right, identity matrix, we mentioned that in class. It's a square matrix that has 1 along the diagonal, right? And then 0 elsewhere, right? 0, 0, 0, 0, 0, 0, 0, like that, right? You have 0 everywhere else, and then all the ones are on the diagonal. Now, what's so nice about this matrix is that, let's say I have some matrix A, right? And then I can multiply by some identity matrix in the dimension that matches with A. And then we will always get the same matrix back, which is A, right? And that is the same thing as doing identity matrix multiplied by some matrix A. You always get A back, right? So that means the I here, the identity matrix, is working as the same way as the number 1 in terms of multiplication, right? This is similar to some number A multiplied by 1, which is A, or 1 multiplied by A, right? So this is in the real number sense, and this is in the matrix sense, right? Now, on the other hand, what we're going to focus on this section is we want to look for the inverse of the matrix A. Now we know it's easy to find the inverse of some real number A. You just take the reciprocal of it and then multiply it by A, and then you get 1, right? But that's not exactly the same as matrix, right? So our goal is to find the inverse of A, which is denoted by A to the power of -1, our inverse of A. Find inverse of A such that A times A inverse will give you the identity matrix, which is the same as A inverse times A. Now, if you guys recall from a few sections earlier, we know that matrix multiplication is not always commutative, meaning it doesn't always give you the same thing when you flip the order. But in this case, if you have the matrix A and its inverse, they are actually commutative, means it doesn't matter the order of the multiplication, you will always get the identity matrix back, right? So this is the tricky part. How do we find the inverse of A? Okay, now let's look at your notes 2.2 and theorem 4. Right, I'm gonna write down theorem 4 here, the notes. Okay, so theorem 4. So it says, let A be the matrix A, B, C, D. okay, a 2 by 2. If AD minus BC is not equal to 0, right? Now notice that AD minus BC is this, right? A times D minus B times C. That's actually the determinant, right? Then A is invertible. Now, invertible, let's do a quick side step, right? Invertible basically means that the inverse exists, right? That means we can find some inverse of the matrix A so that when we multiply A and A inverse together, we get the identity back. Right? And this theorem is very nice. It also tells us what the inverse is going to be, right? So A inverse is going to be 1 over AD minus BC multiply by the matrix D, negative B, negative C, A. Okay, so let's analyze this a little bit. Now, this part, the 1 over AD minus BC, this is a scalar, right? That's just a number. A, B, C, D, they are all real numbers. So 1 over AD minus BC, that's also a real number. And what you're going to do is just take this number and multiply by this matrix in here. Now, this matrix is just the reordering of the original matrix A, right? You switch the place of A and D, and then you add negative signs on B and C. All right, that's it. That's how you can find the inverse of in the inverse of a 2 by 2 matrix. All right, and this part, AD minus BC, if AD minus BC is equal to 0, then we say that A is not invertible. Then A is not invertible, right? Basically means that the inverse does not exist, right? Inverse does not exist. All right. Now, let's go back earlier to talking about the numbers AD minus BC. We say that that is also the determinant of A. So we can write this as determinant of A, DT of A. Now, some people use a parentheses around the A is equal to AD minus BC. Now, determinant of A is actually determinant of a 2 by 2 matrix is pretty easy to find, right? All you do is you multiply diagonally and then you subtract off diagonal like that. Now, for a 3 by 3, it's actually a little harder to find the determinant, but hopefully we won't get there yet. So the idea of using finding inverses is, again, in the beginning of linear algebra, our goal is to solve a matrix equation like this, right? AX is equal to B, where A is a matrix, right? The coefficient matrix. X is your column matrix of all the variable, and B is your constant, right? Now, assume that if we can find the inverse of A, and I'm going to multiply the inverse of A, the inverse of A to both sides, like this. Okay. Now, before we move on, here is something subtle that I really want you guys to be aware of, is that notice that when I multiply the inverse of A, I put the inverse of A on the left-hand side of the equation of both sides, right? On the left-hand side of A and on the left-hand side of B. Now, this is very important because we talked about this earlier, that matrix multiplication is not commutative, right? So the order of matrix multiplication actually matters in this case. So what we're doing here is something called the left multiplication. right? Meaning we are multiplying the matrix on the left-hand side of the equation. Now, of course, you can do a right multiplication, but it's not going to serve our purpose in this case. So let me show you what happens when we do this, right? Now, on the left-hand side, we know that A inverse times A is going to give you an identity matrix, right? Multiplied by X, which is equal to A inverse B. Now, identity matrix, if you take an identity matrix, multiply it by any other matrix, we know that that is going to give you back the same thing, X, right? So in this case, we know that X is equal to A inverse multiplied by B. We can find N inverse very quickly using theorem 4 for 2 by 2. And then we just need to multiply this matrix by the constant matrix B, and then we get our X. Okay, so this is a very nice technique, very nice theorem that we're going to use. And in fact, this is actually theorem 5. If you take a look at theorem 5, that's what this is talking about, right? But again, it's not very easy to find the inverse of matrix if you have a 3 by 3 or higher dimension matrix. For now, we only know how to find the inverse of a 2 by 2. All right, let's look at example 1. I want you guys to take some time and just read over theorem 6. It's pretty straightforward. Yeah, let me know if you guys are having question with theorem 6. Email me or come visit me during my office hour. So example 1. Now I'm only going to do one of them. I want you guys to try the rest. So basically you have four matrices, right? E1, E2, E3, and the matrix A. And here the example is asking us to compute E1 times A and E2 times A and then E3 times A and describe the elementary row operation of A. So basically what we have here is that E1, E2, and E3, they each represent a different row operation. Remember the elementary row operation we talked about in chapter 1? So we can perform those operations using through matrix multiplication. And I'm going to show you the first one, which is E1 times A. And I want you guys to try E2 times A and E3 times A and see what you can get. Right, so E1 times A, first E1 we have 1, 0, 0, 0, 1, 0, and the negative 4, 0, 1. Right, multiply by our matrix A, which is just A, B, C, D, E, F, G, H, I. A, B, C, D, E, F, G, oops, G, H, I. Okay. All right. So a 3 by 3, a 3 by 3 matrix multiplied by a 3 by 3 matrix. Result is going to be a 3 by 3. All right. So let's see. I'm going to put ADG on top of here. Right. Let's do a quick review on matrix multiplication. Right. ADG. That's your first column. Right. So that's just going to give me A. Right. All right. Now move on to the second column. I only get D. To the to the second row, I only get D. And then the third row, I get negative 4A plus G. Okay, interesting, right? All right, let's keep going. Now moving on to second row, right? And then I'm going to put BEH, BEH right here. All right, so first it's going to be B, and then BE, right? And then negative 4B plus H. B plus H, right? All right, next going to be our third column. Oops. All right. So CFI, right? So put CFI here. All right, first it's going to be CF and then negative 4C plus I. All right, so this is our result, E1 times A. All right, so let's do a little analysis on the result. So the first to compare, um, I'm gonna put A on the side here so it's easy for us to compare. Right? So A, B, C, D, E, F, and G, H, I. Okay. All right, so comparing these two matrices, right? The original matrix A and E1 times A. Let's see the main difference, right? So the first two rows are the same, right? We have A, B, C, D, E, F. The only thing that is a little different is the third row. And let's look at what's different, right? We still have the G, H, and I, but notice that we have the extra term negative 4A, negative 4B, and negative 4. That should be C, right? Sorry. I'm gonna erase that. Should be negative 4C. Oops. Right here, C, right? Because C times negative 4 plus I times 1, negative 4C. Okay, so what we have here is actually taking the first row, right, which is A, B, C, multiply it by negative 4, and then add to row 3, right? So let's do this with the matrix, right? If we perform elementary row operation on this, and then we say that R3 is going to become negative 4 times R1 plus R3. Right. So negative 4 times R1, you have negative 4 times A, B, and C. And then add it to row 3, so negative 4A plus G right here, negative 4B plus H right here, and negative 4C plus I, which is right here. Right. So this negative 4 that is in E1 actually represents one of the row operation, which is adding a scalar multiple of the other row to some row, right? So go ahead and try the same thing with E2 and E3 and see what type of row operations you end up with, right? And this is just a quick practice on how to identify elementary row operations through matrix multiplication. Okay, this last part here, I want to show you. Basically, it's example 2, but I'm not going to use the exact. I'm probably going to do only part 2, not part 1. So this is going to be how you can find the inverse of a matrix by hand, right, without using the formulas. Now, if you look at example 2, part 1, it's pretty easy. It's a 2 by 2 matrix. Of course, you can use the definition to you can use the definition to find the inverse, and that'll be very easy. But for 3 by 3, it's going to take you some time, right? So let's go back. Let's go, get started and do what we're going to do. Okay, let me just set up my matrix here, right? So I want to find inverse of the matrix. Set 1, negative 2, 1, 4, negative 7, 3, and negative 2, 6, negative 4. Okay, so this is our 3 by 3 matrix. We want to find the inverse of this 3 by 3 matrix. Now, theorem 7, it tells you how you can do that, but I'm just going to give you a quick idea on what we're going to do. So we're going to set up a new matrix, and I'm going to set it up like this, right? So first, let me copy down the matrix, right? Okay, and then I'm going to split that in half. And on the right-hand side, I'm going to put in the same dimension, which is a 3 by 3 identity matrix, which is 1, 1, 1, 0, 0, 0, 0, 0, 0, like that, right? So on the left-hand side, we have the matrix, let's call that A, and on the right-hand side, we have the identity matrix, okay? Now, our goal is we are going to perform elementary row operation on this entire matrix so that the left-hand side will look like this, right? The left-hand side will become an identity matrix, and on the right-hand side, we will have, you know, some matrix here, right? Because of elementary row operation, we have to perform it on the entire row. So remember that we do this through elementary row operation, or we want to get to the reduced row echelon form. Okay, so let's get started and let's see what we end up with. All right. So let's copy down the matrix again. 1, -2, 1, 4, -7, 3, -2, 6, -4. Okay, and then 1, 0, 0, 0, 1, 0, 0, 0, 1. All right. So let's perform some elementary row operation first. I want to make these two entries 0, right? So R2 is going to become -4 times R1 plus R2. Okay, and then R3 is going to be 2 times R1 plus R3. Right, and let's see what we have. All right, so that's a 0. -4, that's 8 minus 7, 1. -4 plus 3, -1. And then moving on to the right hand side, right? -4 plus 0, -4. 0 plus 1, 0 plus 1, 0 plus 0. Right? And then here's 0, 2, -4 plus 6, 2. 2 plus -4, 2 plus 0, 0 plus 0, 0 plus 1. Okay. Now we want this to be a 0, right? So R3 is going to be -2 times R2 plus R3. 1, -2, 1, 1, 0, 0, 0, 1, -1, -4, 1, 0. Okay, so that's 0. Multiplied by -2 plus 2, 0. Multiplied by -2, that's a 2 plus 2, and plus -2, that's a 0. And then -2, it's 8. Plus 2, that's a 10. -2 plus 0, and 0 plus 1. All right, so one thing that we see here is we actually get 3 zeros on the left hand side. That means it's impossible for us to get an identity matrix on the left, right? So if we see that, then we can stop here, and then we can say that the matrix A is not invertible, right? Because we get 3 zeros here, right? Our goal is to get a 1 here, not a 0, but the setup of this matrix actually gives us 3 zeros in here, right? So we can stop and say that this matrix is not invertible. That's this a good example to see, you know, what happens if a matrix is not invertible. I should have picked one that is invertible first. So let's keep going, and then we'll do matrix 1, part 1, which is 5, 10, 4, and 7. I really want to show you how this works, right? So 1, 1, 0, 0. right? So we have the matrix on the left hand side and the identity on the right, and we're going to do the same thing. All right, so first I want to make the, our goal is again to make the left hand side, clear that. All right, so redo, all right, 5, 10, 4, 7, 1, 0, 0, 1. Okay. All right. So first, let me take row 1 and multiply by 1/5. I get 1, 2, 1/5, 0, 4, 7, 0, 1. Okay. And I want to make this a 0. So row 2 is going to be -4 times row 1 plus row 2. Right. 1, 2, 1/5, 0. That's a 0. That's -8. Right, so -1, no, -4/5 plus 0, -4/5. That's still a 1. Okay. Now I want to make this a positive one, so multiply row 2 by -1. Okay. And -1, so I have 0, 1, positive 4/5, -1, like that. All right, now last, we just need to make this to a 0. So row 1 is going to be -2 row 2 plus row 1. Here we go. 1, 0, 1, 4/5, -1. All right. Now this is still 1 because 0 multiplied by -2 is still 0, and add 1 is still 0. All right, so that's a 2. So -2 times that, that's -8/5 plus 1/5, that's -7/5. -2 times -1, that's a 2 plus 0, that gives you a 2. All right, so now that we started with some matrix A and identity on the right-hand side, we now get to I on the left-hand side, and the matrix on the right-hand side, surprisingly, it's going to be the inverse of A. Now let's check that using the formula. All right, so A inverse is 1/AD minus BC multiplied by DA, DA, negative B, negative C. All right. So let's check this. 1/AD minus BC. So AD, 35, minus BC, 40, multiplied by D, negative B, negative C, and us 5. 5, yeah. Okay, so here we have -1/5 multiplied by this matrix 7, -10, -4, and 5. And let's see what we have. We get -7/5, 2, 4/5, and then -1. Okay, and that is your inverse using theorem 4, which matches with this part, right? -7/5, 2, 4/5, and -1. So for a 2 by 2, it's much faster to do it using the formula from theorem 4, right? But of course, this process here of finding the matrix works on a 3 by 3 matrix, works on a 4 by 4 matrix. Now, of course, given the computers nowadays, we can actually go up to, probably like 100 by 100 matrix to find the inverse of that using a computer. But for now, we're just going to stick to 2 by 2s and 3 by 3s, right? But make sure you know how to find inverse using this process right here, right? But of course, for 2 by 2, you can always do it with the formula, okay? All right. Um, Hopefully this time around the video is a little better than last time. I've been trying out different programs to make my videos. But feel free to, YouTube some other videos on the same topic. I'm sure there are tons of videos out there that are very beneficial to our class. Okay, thank you very much, and I'll see you during office hour.